the video for the beginning of chapter 13. So we start the study of function of several variables. So what have we done so far? In chapter 12, we looked at what we call vector value functions. So functions from R to R3 or R2 or etc. So we had one parameter t, and the output was three numbers for R3, x, t, y, t, and z, t, and that essentially described the position of a point in space. Okay, and so that those were vector valued function because the output is a vector. Now we're going to look at we also looked at surfaces. Okay, so we saw plane, flat surfaces, we saw quadratic or quadric surfaces, and also surfaces of revolution. And essentially a surface is what? It's a set of x, y, z, right, that satisfies some relation. For example, a sphere has this relation. Okay. Some of these surfaces the equation was the equation of a function, and actually that's what we're going to look at more carefully. So we now narrow the study of the surfaces that are defined by function. Okay. So essentially, we're looking at a function now, a two variable, f of x, y, and we can graph those in 3D by taking the output z as the third coordinate. All right. So this is now a function of several variables, x and y. So we're going to look at functions of R2, so two input, x and y, and one output, r, that we can graph in the third dimension. All right. But there's nothing that prevents us, and actually the calculus works as well, to study function of Rn to R, so function of several variables, n variables to R, okay? Everything I'm going to say works there, okay? It's just that it's a bit more awkward to graph this function in 3D, all right? Because, well, I need n plus one dimension, n dimension for the domain, the input, and one dimension for the output. So at some point I run out of dimension, right? So, but those functions exist, they're fine, it's just that you cannot graph them the usual. All right, so those functions have the same kind of concepts attached to them. And that's what we're going to do for the next couple of weeks, okay? So let's start with the basics, that is, what is the domain of a function, what is the range, and look at continuity, okay? So the domain is exactly like in 1D or in any mapping, any function. So the domain is a set of input. In our case, the input has two real numbers where the function is well defined. Okay, so this is the domain, and the range is the set of all outputs you get from the domain, from all the inputs. Okay, all right. So let's do an example. So what is the domain of this function? So this function is 16 minus 4x squared minus y squared square root. So this is the usual question you get in calculus 1, except we have two input here. So the domain, I have a square root, so you have to look for quotients and square roots, and where some functions are not well defined. So here in the real numbers, the square root is not well defined for negatives. So I want what's inside the square root to be positive. So we want 16 minus 4x squared minus y squared to be strictly positive, not strictly, or 0. And so if I rearrange this, this is the same as saying that 4x squared divided by 16 plus y squared divided by 16 is smaller or equal to 1. Okay. Now, all right. I'm just gonna delete this. Okay. And so therefore the domain, we can actually draw in R2, right? It's a region of the plane now. So domain, this defines a region in the plane where all the outputs of the functions are well defined. So this defines a region of the plane. And what's that region? Well, if you look at the equation, it looks like an ellipse. And it is an ellipse, at least the boundary of it, the border of it is an ellipse. Okay, so the border is equal to 1, and the region is defined by small or equal to 1, so this is what's inside the ellipse. All right, so then the x region actually is from, if you think about it, -2 to 2, and the y goes 4 to -4, and let me see if notability is good to me. Not so good. Bit better. I'm going to stretch it. Doesn't work. I want an ellipse. Better. It's a bit tilted. So, shouldn't be tilted. And so the domain, it's what's inside the ellipse. So that's the domain of the function. Okay, so the difference now is the domain is a subset of R2. So it's more interesting than in one variable. Okay? Now what about the graph of that function? Well here, so what's the graph? So the graph is in 3D. So actually let me move this down. Okay, so the graph is in 3D. So the graph is all the point x, y, and z, and now, again, this is how we decide to graph things. X, y is an input, and z is the output, so where z is equal to the function of x, y. Okay, that's how we draw things. So if you look at what it is, okay, so z is equal to 16 minus 4x squared minus y squared, and if to remove the square, I can square the z, and so what I'm going to get is actually an ellipsoid. So that's an ellipsoid. However, you have to be careful because an ellipsoid has two caps, right? There's a positive and negative part. So this is not the graph of a function. However, here is the positive square root. So it's the upper cap of an ellipse. Okay? So we could recognize the graph of this function just by looking at it and by knowing what an ellipsoid was. But in general, to get a sense of a graph in 3D, what you can do is level lines. And by the way, this also works in higher dimension. Okay, so you would look not at level lines, but level shells. Okay, so what are level lines? Well, it's all xy such that the function equals a given number. Okay, so for example, the level lines of my function here would be, so now there's infinitely many level lines, so you just choose the levels. So for example, z equals to 0. So what xy gives you a value 0, in that case would be, so all the xy such that fxy is equal to 0. And so if you look at it, what you're going to get, it's 4x squared minus y squared square root equals to 0. So you're also going to get an ellipse. And z equals to 1 would be 16 minus 4x squared minus y squared square root equals to 1. You also get an ellipse, but which is slightly smaller. Okay, so the level lines would be, essentially, I'm going to move that figure, I'm going to move that figure and make a comment. So really, if I draw the level lines, let me do a good job here. If I draw the level lines, okay, so you have I don't know why it doesn't like always tilted. It's a bit better, isn't that great? Okay, so that's, let's say, all the xy such that z equals to 0. I'm gonna duplicate this one, and I'm gonna make it orange, and then I'm gonna scale it a little bit. Okay, and so if you solve this equation, this is gonna give you an ellipse, not solve but simplify, and it will give you an ellipse which is inside. Okay, so what we're doing essentially is slicing this ellipsoid, the upper cap of the ellipsoid, and looking at the line you get, and this is why it's called the level line. So this is not new, because this is exactly what you get in a topographic map. Okay, so a topographic map gives you the height, the information about the height on a two-dimensional map. So it's exactly what we want to do here, is give information of the height, so of the z coordinate, but on a plane, so on a map. Okay, so what happens here, those lines represents the lines that are at the same height. Okay, so this is like a mountain or maybe a valley. Okay, and if you follow that line, you're going to stay at the same level. Okay, so just slicing, and then if you look at the other line here inside, it's also at the same level, etc. Okay, so this topographic map really has the information about the height of the mountains or the valleys, right? And it does it with level lines. We're doing the exact same thing here with that graph, all right? Okay, so we'll practice that in the exercises. Now, the other notion that we know from basic calculus in one variable, is continuity. So a smooth function, okay? So what is continuity in 1D? So when you have one variable, we say it's continuous at a point x0. So here, this is my input and this is my output. So y is now the output, okay? And this is my function f of x. Okay, so that's how we represent that function. Y is, the y coordinate is the output of the input x. Now we say that f is continuous at x0 if, when you approach x0, the limit is exactly f at the point x0. Okay, so in my picture suggests that the function is continuous. Okay, now the important point here is that this limit has two sides. I can approach from the left or I can approach from the right, and we say the limit exists if they're both equal. Okay, and we say it's continuous if this number, which is the same for both one, also equals f of x0. Okay, so we have kind of, for continuity, we need a triple equality, a double equality. Equality of the limits for the two approaches, and this number should equal also the value of the function. Now, here where it gets tricky, and we have to appreciate what it means to be in higher dimension. Higher dimension means more room, it means more possibility to approach a point. Okay, so let's say so now my plane is my input, right? An input is a point x and y. Okay, so now how can I approach that input x0, y0? Well, I'm on the plane, so I can approach it from several directions. So this limit, when I approach x0, y0, means a lot of limit, more than 2, infinitely many. Okay, I can approach a point from infinitely many directions. Okay, so it's more tricky to establish that a function is continuous. Okay, so more generally, we say that xy approaches x0, y0 if and only if the distance, okay, between x, y, and x0, y0, that's the distance, tends to 0. Okay, but of course, there's many points that are the same distance, and again, there's several directions to prove that point. Okay. So what's the definition of a continuous function? We want that the limit when x, y approach x0, y0 of the function. So no matter how you approach the point, okay, the limit you get for any direction is the same, and this number equals the value of the function. Okay. By the way, it's the same definition, and instead of R2 you have Rn. It's just that, well, distance is different in Rn. All right. Now, we won't enter into the delta epsilon terminology of continuity. I just want to give you a feeling, intuition of what continuity means and what are the pitfalls, okay? So exactly as in 1D, if you take a product, a sum of continuous function, it remains continuous, okay? So continuity is a nice property. If you have a quotient, so you divide by a continuous function, you just have to be careful that what you divide with is not 0, okay? But essentially, if you do basic operation with continuous function, it remains continuous. Okay. Now let's appreciate how tricky it is to approach a point, okay? And here's a good example, and we'll do more in class. Let's take the rational function x minus 2y divided by x squared plus y squared, all right? This is a function of xy, and obviously there's one point where it's not defined, okay? So the domain of that function is the whole plane. The domain is the whole plane, R2 minus, well, the point 0, 0, obviously, because that's the point where I divide by 0. Okay, so the function is not defined at 0, but maybe the limit going to 0 exists, okay? And then I could actually, I could take this limit as my definition of my function at 0, now I would have a continuous function. But the limit does not exist. So how to show that the limit does not exist? Well, you have to pick two ways to approach the point where you get different values, okay? So again, it's not only left and right limit. There's many directions, so to show that the limit does not exist, you just have to find out two directions among this infinitely many choice where the limit does not exist. Okay, so let's first approach the point on the path y equals to x. Okay, so you take the line y equals to x. Okay, this is that line. I'll put two colors, you'll see why, for the positive or negative. Okay, so I'll approach, let's say 0, 0 on the path y equals to x, taking x small, and here I approach from the negative. Okay, so these two paths. What do I get? Well, now I can do the algebra, because approaching on that path, I just replace y by x. So I replace x minus 2x, I get minus x. So I get minus 1 over 2x. Oh, so if I approach from the positive 0 plus, I get minus infinity. If I approach for 0 minus, I get plus infinity. Okay? So the limit does not exist. I get two different directions. So, okay, you're going to say maybe it blows up on both sides. Okay? Like you get functions in R plus going like this, you know. So functions in R, these kind of asymptote. It's worse, because if I take the path y equal x over 2, so what's the path y equals x over 2? It's slope 1 half, so it's like this. So I approach the point, but slightly different direction. Now what happens is y minus 2y, when I plug it, it gives me 0. And the denominator is non-zero when I approach. So this so this is 0 for any x on that path, except the origin. So when I approach, it is 0. Okay, so the limit when x goes to 0 of the path fx x over 2 is 0. So it's not only that it blows up on this path, but on the other path it's 0. So how can that be? Well, we're in 3D, and I put the graph to help you. This is what this graph looks like, okay? So I invite you to do it by yourself. So what happens is that this is the path y equals to x, okay, this line. Okay, so depending if x is positive or negative, you're going to blow up like this or you're going to blow up like that. However, if you approach it just the right way, like this, okay, then the limit's going to be 0. All right? So you see that you have singularities that are much more interesting in higher dimension. Okay? The geometry is much, much, much richer, and we're going to see that. Okay, last remark, to actually determine the limits, sometimes, and there's some examples of that in the homework, I'll do example, it is useful to use polar coordinates when you approach the origin. Just because approaching the origin means the distance tends to 0 and the distance is simply r. So sometimes you can replace the whole limit you want to evaluate. You can replace this quantity by r and simplify the problem. Okay, it's just a small remark. All right. Okay, so thank you for listening.